For day 11, we learned that an alien visits Earth and discovers she's able to jump incredibly high. So what does that mean right off the bat? If she's able to jump incredibly high, if it seems high to her, then gravity must be lighter, like it is when an astronaut goes to the moon. So what we're expecting is then on Earth, there is our gravity, and on their planet that it comes from, gravity is larger. It is greater. So it's greater than 10 meters per second squared. And on Earth, of course, it's 10 meters per second squared. So it speculates that on the free fall accelerated Earth is different from that on her home planet. Well, yeah, it's different, and it must be larger because it's easier for her to jump higher. She's stronger. She's used to working in a harder gravity environment. Her home planet is twice the diameter of Earth, but made of material with the same density. All right, so we have the Earth of a particular size, and that planet has a diameter twice as large. So let's consider, they bring in the concept of density, and density, rho, is mass divided by volume. And so if we consider Earth and the planet, it says the densities are the same. So the densities are the same. So that means the ratio of the mass of the Earth to the volume of the Earth is the same as the mass of the planet to the volume of the planet. Clearly, the planet is larger. It has more volume. It also has more mass, but they are they're proportional to each other. The ratios are proportional to each other, or equal to each other, excuse me. So let's do, we want to know G, the acceleration on the home planet, we know, first of all, is greater. So G is greater. That's the first thing we want to say. We've at least given a qualitative answer. So G for the Earth, let's make the Earth green. Oops, Earth green. And the planet red. So G for the Earth is big G, big M, over R squared. And this is the mass of the Earth, the radius of the Earth, G of the Earth. And we know that the planet, the G on the planet, is going to be equal to G, which is the same in both places, mass of the planet over R of the planet squared. Now what we know is if we have the R of the Earth, that the R of the planet is twice as large. So RP equals 2RE. So we could do that substitution. GMP over RE 2RE squared. So we've now got similar terms, RE and RE. The G's are the same, so now we just need to know the mass of the planet in terms of the mass of the Earth. And that's where the density comes into play. So we have the mass of the Earth, the volume of the Earth, the mass of the planet, the volume of the planet. Well, we know the shapes of these things are spheres, and the formula for a sphere, volume of a sphere, is 4/3 volume of the sphere of the Earth is 4/3 pi R of the Earth cubed. Similarly, we know the volume of the planet is 4/3 pi R planet cubed. Well, we know our planet is 2R Earth, so that means we have 4/3 pi 2R Earth cubed. And it's important that we view this as one quantity. Otherwise, we're liable to make a very big mistake. All right, so we have this new expression here. We want to know about G, and we're looking for the volumes. And mass of the Earth, our ratio, mass of the Earth to the volume of the Earth equals the mass of the planet to the volume of the planet. And really, this is what we're looking for, is this mass of the planet. That's what we need. That's what's missing in this comparison, is the mass of the planet. So we solve for MP, and that is ME VP over VE. All right, so the mass of the Earth is a constant we pull out. The volume of the planet is 4/3 pi 2re cubed is 8re cubed. And the volume of the Earth is 4/3 pi re cubed. So of course now we can see the 4/3 drop out, the pi's drop out, the re thirds pop out. So the mass of the planet is 8 times the mass of Earth is 8 me. So then when we compare these, we have G 8 me over 4 re squared. And so that reduces to G 2me over re squared. So when we compare these two numbers, what we can see is that G of the planet is twice the value. The number that's different, we got G, me, re squared, re squared. The difference left is 2. So it's twice the acceleration caused by gravity. There's a lot of algebra here and a lot of substitutions, but this is a very commonly used approach, particularly in astrophysics things when quantities are not known. You notice we could tell relatively how large this planet is, how massive this planet is compared to the Earth without even knowing how large our own Earth is. And so that is day 11.